today we're going to start section 7.8, which you did pick up notes for both today and tomorrow. That's what's in this packet. And this is the last section in chapter 7. We do have our chapter test. It's only going to cover the second half of the chapter. 7.5 to 7.8 will be Friday. Okay, so we'll finish up notes tomorrow and then review. So today our goal is to graph the square root and other radical functions. So we know in general that the square root graph looks like a starting point that kind of shoots off, right? We're going to graph those with translations today, so shifting left, right, up, and down, using a lot of the rules we already know from chapter 5. We'll also graph radical functions, which could be cube root functions, which look a little bit different. So on this front page, I have kind of the parent function and then its inverse, both the equation and the graph, so we can look at this. And I'd like us to go ahead and discuss what the domain and range, because that's really important as well to be able to identify. So the first one is our quadratic, f of x equals x squared. What would the domain of that function be? All real numbers, very good. Or you can have negative infinity to positive infinity, and that's because the arrows are on both ends going outward into negative and positive infinity. Now the range is not going to be all real numbers. There's two ways that we can write it, either using an inequality symbol or using our brackets and parentheses. Because you can see along the y-axis it never touches a negative number. So what would I write for my range? Yes, our y's need to be greater than or equal to 0. And if you want to state also all real numbers such that y is greater than or equal to 0, that will work too. Now if you like the bracket parenthesis, that would be bracket 0, comma, infinity parenthesis, so if you prefer that one. The book answer key tonight will, the book answer key I think does it this way tonight. But just know you're correct. Now, remember the inverse function, in theory, should swap the domain with the range. So the domain of this function should become the range of this function. Bless you. And the range should become the domain.
Would you write it as infinity comma 0?
Say again?
Would you write it as infinity 0 domain?
For the domain, no, you would still have 0, comma, infinity. Because the smallest the x value ever is 0. The largest it ever gets is infinity. So you would leave that the same. Or again, you could say x is greater than or equal to 0. Okay, so when you do switch this, you do have to switch your variable, because domain is your x values and range is your y's. So we can see the original equation is a function. This would pass the vertical line test, right? But the inverse would fail, right? So what you can do is you can restrict the domain so that both of them are functions. And that's what our graphs are going to look like a lot of times. We're not going to have the sideways parabola, we're just going to have one of those pieces. So either a positive square root or a negative square root, not both. So it says here you can restrict the domain of f so that its inverse is a function. So instead of saying the domain is all real numbers, you actually state a restriction with the domain, which we did this a little bit on Friday. So that you're only really examining a part of the graph instead of the whole thing. That way, when you take the inverse, you're also only going to have half of a parabola, meaning that this will pass the vertical line test and it will be a function. Okay? So our domain and range are going to be different since we stated the restriction. So the domain, they've already restricted it for us. X is greater than or equal to 0. You also could do bracket 0, comma, infinity. The range is actually going to stay the same as it was in the one before. Our y values have to be greater than or equal to 0. So for our inverse function, those are going to move to the opposite spots, but they're both the same thing. But let's make sure it makes sense. Our x values are going to be greater than or equal to 0. and our y values are also greater than or equal to 0. So this is what we're going to be graphing today. Now, to make it faster for us, we may want to notice a pattern. Like when we used to do quadratics, we would go up 1 over 1, up 3 over 1, and plot the points instead of having to like check a table every time. So if you want, you can notice a pattern with these. They do start at 0, 0. Our origin. Now in the back when we're graphing them, we may be shifting that left, right, up, or down, depending. But then it goes up 1 over 1, and that's a point. And then to get the second point, it goes up 1 over 1, 2, 3. And that'll get you enough points to be able to sketch your graph kind of quickly so that you don't have to do a table of values every time. Okay. The next type of graph are our cubic and cube root functions. Okay, so we see our cubic function, which we used to see these in chapter 6, and they looked a little bit more like this, where it like drastically went up and came down and then went back up again. With the parent function, just x cubed, it doesn't do that. It just kind of is really steep and then it comes up and kind of levels out a little and then goes up. So if you want, you can always, and I do kind of suggest a table of values for your cubic functions just because they're a little bit harder. So just thinking about some numbers we could plug in that might fit on the graph, just -2 to +2, and just evaluate by plugging those in. And just so you realize, any question you don't know how to graph, you can create a table of values at any point and do this, and then you can graph it. Obviously our graphing calculator can do it for us in the table feature, but. So -2 cubed, -2 times -2 times -2 is -8. -1 cubed is -1, 0, 1, and 8. So you can see that really on this little graph piece that they gave us, only 3 of the points are able to be plotted. So you have to be really careful with these because if you did just plot those, you might think it's a straight line. Okay, so you might want to do one that goes even off the graph just to give yourself an idea of what it's going to look like. Now, for the inverse function, remember this is going to be, to get your inverse, it's going to be reflected across the line y equals x. Well, these happen to fall on the line y equals x. So notice, these points are exactly the same. So when you go to graph the inverse, you're going to think, oh, it looks exactly the same if you don't come up with those other points. Remember that the inverse flip-flops the y's and the x's. So your inverse should have points -8, -2, -1, -1, 0, 0, 1, 1, and 8, 2. So the big difference is that additional point is going out to 8 and up to 2, or out to -8 and down to 2. So you can see that it's kind of been flipped sideways. Usually for your cubic graphs, I'm going to suggest that you just create a table of values to help you understand what's going on, but it is good to have like a mental image of what it should look like. All right, it says the inverse of functions in the form y equals x to the n power form parent functions in the form y equals the nth power of x. So you can see, you know, your cubic, the inverse is the cube root, and that only works if it's just the parent function. So another example would be like h of x equals x to the 4th. So the inverse h prime of x would equal the 4th root of x. So we're going to practice graphing using some translations, shifting left, right, up, down, and also look at some vertical and horizontal stretches and shrinks. All of this stuff is pretty much the same as what we learned in chapter 5. So you have your parent function y equals the square root of x, and we know that that kind of looks like a starting point that jets off into the positive. If you see a negative in front, remember that's a reflection downward across the x-axis, which means the graph would then reflect downward. Now the a variable in the front tells us if it's a stretch, which is if a is bigger than 1, so 2, 3, 4, 2.5, or it's a shrink, if A is between 0 and 1. So an example of a stretch, just like to give you a little picture, would be if the graph went like this. So it still jets off, but it's like it's increasing much faster, I should say. A shrink would be that it actually gets like more shallow. So it's being vertically shrunk instead of kind of increasing at such a fast pace. It's increasing at a smaller pace. Now this one, just get rid of it. The reflection and the x-axis we already have, and they were kind of combining the stretch and the shrink. I'd rather you do those separately. Anyways. And then the big thing is down here, whether you're adding or subtracting inside the radical or outside. So who remembers if you are subtracting like inside of the quantity, what direction shift does that make? Right?
The right.
Very good. This would be to the right. And that's because it's under the radical, and it does go in the opposite direction that we normally think. So if you did have the absolute value of x plus h under the radical, that would be to the left, h units, however many h is. The plus or minus outside the radical is up or down. So this right here would be up. Obviously, if we had a minus k or subtracting k at the end, it would be a down. And then you can combine them and have left and up or right and down accordingly. But you just need to recall those little rules from chapter 5. So down here they ask us to graph each parent function. Just graph the functions. You don't have to graph the parent functions. You just want to keep those in your mind. So with the plus 5 outside, which way am I shifting my graph? Up. Good. So this one's going to go up 5. This one's going to go down 7. So we're doing 2 graphs on one piece of graph paper. So again, you want to hover your pencil at 0, 0, and that's the point that you're doing the shifting because that's where it normally starts. So I'm going to go up 5, 2, 3, 4, 5. And then you're going to use your pattern, which again is up 1 over 1, and then up 1 over 3. If you forget the pattern, just do a table of values. Just pick numbers to plug in for x. And then you will sketch the curve as best you can. Put an arrow on the end. It's kind of like a ray almost, but it's not straight, so it does have just one-sided arrow. Now think about why this makes sense. This is 4, right? So if I were to plug in 4, the square root of 4 is 2. 2 plus 5 is 7. So again, if you forget how to graph, just plug in numbers, and I would pick ones that are perfect squares. And then for the next one, the minus 7, we're going to, again, start at 0, 0. We're going to shift down 7. So down 1, 2, 3, 4, 5, 6, 7. And then follow your pattern again. Up 1 over 1, and up 1 over 1, 2, 3. I'd like you guys to try 2, 3, and 4 on your own using the rules. Pay attention that in 3 and 4 you are shifting left or right because it's underneath your square root. Should be getting some graphs that look something like this. If you want to extend yours further, you can. I mean, we don't know exactly what it goes like after that unless we plug in some more values, but you're welcome to extend it like with a sketch if you'd like a little bit further. But basically just so I could make sure that they were distinct, I didn't overlap them. So just make sure that again, whenever you're inside, that you are doing the opposite. This plus 7 should go to the left, the minus 5 went to the right. So on the next page, what we're going to do is we're going to combine left, right, up, and down, also with some stretches and some shrinks. So what that's going to affect is if we have like a 2 in front of here, that's going to affect our pattern and how we're counting. And so a combined transformation looks something like this. Again, A is the vertical stretch. So again, that's making it like steeper. And a shrink would be making it less steep or increasing at a slower rate. So that is going to affect how we count like up and over. And we're also for these ones going to state, domain, and range as well. So this 3 in the front is telling me that it is a stretch by a factor of 3. And then I also have some translations inside. We have a shift left 2 and down 1. Okay, we're going to do these without a graphing calculator, and then I will show you too how it could help us. Now, when you're doing this, you do want to apply your shifts first. Because the stretch or shrink doesn't affect that starting point, it just affects the subsequent points. So again, we'd normally start at 0, 0, we're going to go to the left 2, and we're going to go down 1, so I'll put a point right there. And then we're going to modify our pattern using the stretch or shrink, okay? So it's going to change our first movement, our up or down. So we're actually going to go, instead of up 1 and over 1, we're going to go up 3 and over 1. Normally we then go up 1 over 3. We're going to instead go up 3 over 3. So this number is really affecting how much we're going up or down. The other numbers are going to stay the same. And then we're going to connect that as best we can. Now be aware on the graphing calculator, sometimes when you look at the graph, like this graph in particular, you can't really see this part on the graphing calculator for some reason unless you zoom in. So you may want to, if you do use the graphing calculator at any point, I already have it typed in from an earlier class, it looks like it just stops at 0. Okay, but if you do check your table, you'll see -2, -1. -2, -1. So like it does exist, just be aware of the graph that you either zoom in or use your table feature. While we're here, real quick, some people have been asking me about their table because it's blank. Okay, remember if you need to change your table set, you'll press second window. And some of you may still have the ask turned on from whenever we used to type in numbers and have the calculator run the calculation for us. So if you want it to go back to filling in for you, you just have to go down to auto and hit enter and make sure that those are turned on. Just in case anyone gets stuck with their table, that's one thing you can do to reset it. All right, now the next one on our notes has a shrink of a factor of 1/4. So again, that's going to change this number. Instead of going up 1 over 1, we're actually going to go up 1/4 and over 1, which is going to be hard to graph, but we're going to do it. And then we have a -2, which is a shift to the right 2, because it's under the radical. And we're also going to go down 4. So for this one, we will go to the right 2, and we'll go down 4. And then again, we're going to go up 1/4 and over 1. Now this is going to be really hard. So counting on fourth spaces isn't the easiest thing we've ever done. And then normally we would go up 1 over 3, but we're going to go up 1/4 over 3. Again, the thicker my pen is, the harder this is making it even to do. But it should look something like that. Again, it's like much flatter than the other normal square root. All right, now be careful on 7 and 8. They switch to cube roots. Oh, we forgot domain and range. Let's go back. Okay, we have to find domain and range for each one. So let's look at 5 first. Now the rule for domain still works. You can still use our rule that the radicand must be greater than or equal to 0 if you want to do it algebraically. So you could say the x plus 2 that's under my square root has to be greater than or equal to 0. And solve, subtract 2 on both sides, you'll get x is greater than or equal to -2. That's for my algebraic people. My visual people are just going to look and say on the x-axis, what's the smallest it ever gets to, -2. and it's going greater than that. If you prefer, we could still do our bracket notation, -2 comma infinity. Now the range starts at -1 on the y-axis, and then it increases to a positive infinity. So we'd have y greater than or equal to -1, or -1 comma infinity. Who thinks they could tell me the domain for number 6? Evan? 2. What about 2? Good. Greater than or equal to 2. And how about the range then? Y is greater than or equal to? Evan? -4. Very good. All right, now the last two, as I said, are cube roots. Okay, these are the ones that are going to be that sideways S shape, which are harder to graph. I would suggest you do a table of values. Okay, we could also describe this is going to be a reflection, 1 unit to the left. This is technically a +3, so it would be up 3 units. But again, it's going to be hard for you to move something that was like -8 all the way off your graph, so on and so forth. So I do suggest creating a little table of values and just plugging in. All right, now you need to think about numbers that you can plug in that will get you perfect cubes. So for instance, I wouldn't plug in 0 because 0 plus 1 is 1, and I don't know what the cube root of 1 is. Okay, so I would maybe start with -1. Because -1 plus 1 is 0. The cube root of 0 is 0. 3 minus 0 is just 3. Let's try -2. If I plug in -2 plus 1 gets me -1. The cube root of -1 is still -1. So that'd be 3 minus a -1, which turns to a positive, and I would get 4. Oh, I could do 0, excuse me. I do need the cube root of 1. I was thinking 2. We can't do 0. We'll get, bless you, the cube root of 1, which is just positive 1. So 3 minus 1 will get me 2. All right, now when we plot those, it looks like it's a straight line, right? Remember, that's what we saw in the graph. We kept thinking it looks like a straight line. But we're going to need some other points to at least be able to figure out. It's going to look like an S shape, but maybe just to give me a better idea. So I'm going to pick something bigger on the x-axis, but I need to get it to be a perfect cube. So after 1, the next perfect cube is 8. So what number plus 1 gets me 8? 7. So you're going to have to do a little bit of logic to figure out what number you're picking. So 7 plus 1 is 8. The cube root of 8 is 2, and 3 minus 2 is 1. And that'll at least give you an idea of like where the other one's going to go off the graph, most likely. But you can get a better idea of your graph right there. Domain and range for this one should be all real numbers for both, because the arrows on both ends are going on forever and ever and ever, both in the x direction and in the y. We're not going to get a chance to finish 8 because the bell's going to ring here in just about a minute, but you would do the same process with that one. And if you'd like, you can check my teacher page to see how that one looks. Homework is 7.8, worksheet number 1. There's only 2 cube roots on there. Most of them are square roots, and you pick that up on your way in.